This is the 9th section on chapter 12, which is on differentiation, and this section is on stationary points. So what is a stationary point? Well, a stationary point is a part of a graph where the gradient briefly becomes zero. So there are three types of these points where the gradient briefly becomes zero. So if you look at the first one here the gradient is zero, indicated by that purple dotted line. And this is what we call a minimum. Now, if it's just a minimum for part of the graph, not the whole graph, then we call it a local minimum. Here's another type of stationary point. So here you can see at this peak here, the gradient is briefly zero, indicated by the purple dotted line. And this we would call a maximum. Now, if it's not a maximum for the whole graph, but just a maximum for part of the graph, then we call it a local maximum. Then the other type of stationary point is what we call a point of inflection. So here we've got a graph that's increasing, it levels off, briefly becomes zero, and then continues increasing. This we call a point of inflection. And with all of these, if we know the equations of these graphs and we work out the derivative at this stationary point, the derivative will be equal to zero. So there are actually two ways that we can identify these stationary points without actually having a sketch of the graph drawn, just from the equation of the graph, and we're going to look at both of those ways. So the first way is by considering or looking at the gradient close to and either side of where we find the derivative is equal to zero. So for example, here what I see is that the gradient this side of the stationary point is sloping down, so it's negative, then it's zero, and then it's positive. So what I've got on the first one here is a negative gradient here, then zero, and then a positive gradient. So if I see this pattern of a negative gradient, zero, positive gradient, I know I've got a local minimum. Here, what's happening on this side of the stationary point is that the graph is increasing. There I have a positive gradient, then here I have a zero gradient, and then the gradient becomes negative as the graph slopes downwards. So if I see this pattern of positive, zero, and then a negative gradient, I know that I have a maximum or a local maximum. Here, however, with the point of inflection, in this example, the gradient of the graph is positive, then it's zero here, and then it remains positive. Now I've drawn a point of inflection that goes up like that. It could be a point of inflection that goes downwards, so it could be starting this way, going down, going across, and going down like this, in which case the gradient would be going from being negative, then zero, and then negative again. Now if I see either positive, zero, positive, or negative, zero, negative, I know that I've got a point of inflection. Now the second method of identifying the types of stationary points we have is by considering the second derivative. That means differentiating the function that gives us the curve twice. And when we differentiate it twice, we'll put in a value of x, and that value of x will be where we have the stationary point. So the x coordinate of the stationary point, that goes in here. If we work that out and we get a number which is positive, we get a greater than zero value, that tells us that our stationary point is a minimum or a local minimum. If we take this value of x and we put it into the second derivative and we get a value which is negative, it's less than zero, that tells us that we have a maximum or a local maximum. If, however, we put that value of x into our second derivative and we get zero, then we need to go to the either side method, that's this method here, to help us identify what type of stationary point we have. That's because with the second derivative equal to zero, we are not able to identify whether it's a maximum, a minimum, or a point of inflection. So we need to go back to this method here, and then we'll be able to decide which one of the three it is. Example 16, part A, find the coordinates of the stationary points on the curve with equation y equals x to the power 4 minus 32x. Okay, so we've got y equals x to the power 4 minus 32x. So if we're going to be identifying stationary points, we need to differentiate and we need to find out when dy dx equals 0. So if we differentiate, we'll get 4x cubed minus 32. And what we want to do is the stationary points will occur when dy dx equals 0. So that will be when 4x cubed minus 32 equals 0. So from that we will get 4x cubed equals 32. We'll divide both sides by 4. So we'll get x cubed equals 8. And cube rooting both sides will give us x equals 2. Okay, we need the coordinates of the stationary point. We've only got the x coordinate, we want the y coordinate, and to get the y coordinate we'll put x equals 2 into the equation. So that'll be y equals 2 to the power 4 minus 32 times by 2. So that will give us y equals 2 to the power 4 is 16. 32 times by 2 is 64. So the y coordinate is going to be 16 minus 64, which gives us negative 48. So the coordinate of this stationary point is 2, negative 48. Okay, let's move on to part B. Part B says, by considering the points either side of the stationary point, determine whether it is a local maximum, a local minimum, or a point of inflection. So part B. So we want to choose points, x coordinates, either side of 2, which are close to 2. Now I wouldn't choose things like 1 and 3. I would choose things like 1.9 and 2.1. So fairly close. So let's say by considering x equals 1.9 and x equals 2.1, we'll use that to help us identify the type of turning point that we have. So what we're going to do is we're going to put these x values into the derivative dy dx and see whether we get positive or negative values. So when x is 1.9, dy dx is going to be equal to 4 times by 1.9 cubed minus 32, or equals 32 minus 32. And that gives me a value of negative 4.564. And now we will look at what we get when we put in x is 2.1. So dy dx is going to be 4 times by 2.1 cubed minus 32. And that gives us 5.044. So what have we got? So before we get to the stationary point here, the value of x is negative. So we get a negative value there. Then after the stationary point, we get a value which is positive. Now what does this mean? Well, it means the gradient is going like this. It's going negative, then 0, then positive. Now how's that going to happen? Well, we get a negative gradient when the graph goes down. We get a 0 gradient at the bottom there, and then we get a positive gradient here. So we've identified the type of stationary point, and it's a local minimum. Negative gradient, 0 gradient at that point there at 2, and then positive gradient. So I could probably put when x is 1.9, we get that. When x is 2, we get 0, and when x is 2.1, we get that positive gradient. So the stationary point is a local minimum. It's a local minimum. There may be minimums elsewhere in the graph that may be even lower, than that, or the whole graph may go lower than that minimum, we don't know. But for this part of the graph, it's a minimum. That's why we call it a local minimum. We would only say it's a minimum if we can be sure that this is the only minimum in the graph, because it could be this graph goes like this, and then there's another minimum a little bit further that goes even further, or the whole graph may carry on going down. We don't know. Example 17. Find the coordinates of the stationary points on the curve with this equation. Okay, so part A, we have y equals 2x cubed minus 15x squared plus 24x plus 6. So if we're going to be identifying any types of stationary points, we need to differentiate. So if we differentiate that, we'll get 6x squared minus 30x plus 24. At stationary points, we will have dy dx equals 0. So we set 6x squared minus 30x plus 24 equal to 0. So this is going to be a quadratic. Let's divide everything by 6. Everything can be divided by 6, so we end up with x squared minus 5x plus 4 equals 0. So this can be factorized. So I'll have x in both brackets. Now we want to get 4, so it's going to be 4 and 1 if we want to get 5. And they both need to be negative. Okay, so this gives us the roots, the actual x values as x equals 1 and x equals 4. So these are the x coordinates where the stationary points are. We now need to find the y coordinates. So y equals, so we'll do the x coordinate of 1 first. So 2 times 1 cubed minus 15 times 1 squared plus 24 times by 1 plus 6. That gives us y equal to 17. And we'll do the same for the other x value of 4. So 2 times 4 cubed minus 15 times 4 squared plus 24 times by 4 plus 6. And that gives us a y value of negative 10. Okay, so the coordinates of the stationary points, are 1, and with the x value of 1 we've got a y value of 17, so don't make sure you don't mix them up. So 117, and the 4 went with a value of negative 10. So those are our stationary points, 117 and 4, negative 10. Now in part B, it says use d squared y over dx squared, the second derivative, or find it and use it to determine the nature of the stationary point. So let's find that first. Let's find the second derivative. So that means taking the first derivative, which is this 6x squared minus 30x plus 24, and differentiating that. So we will get 12x minus 30. So what we're going to do now is we're going to plug in x equals 1 into it, and then x equals 4 into it, and see what sign we get. Do we get a positive or a negative value? That will tell us whether it's a maximum or a minimum. So let's put 1 into this. So we'll get the second derivative, d squared y over dx squared is going to equal 12 times by 1 minus 30. So that gives us negative 18. And then we will put in the 4 into that. So 12 times 4 minus 30. So that's going to be 48 minus 30. So that will give us a positive 18. Right, so because the second derivative here is negative, that tells us that when the x value is 1, what we have is a local maximum. So because this is negative, at the coordinate 117, we have a local maximum. So it's always the opposite to what you think. Negatives is maximum, positives is minimums. Here, because the second derivative is positive, and it was the x value of 4 that gave us this positive value for the second derivative, that means for the x value of 4 and the coordinate 4, negative 10, we have a local minimum. So just remember, positive minimum, negative maximum. It's the opposite to what you think. Example 18, part A, the curve with equation y equals 1 over x plus 27x cubed has stationary points at x equals plus or minus a. Find the value of a. Right, so that means we're going to have to differentiate this. So we want to write this in the form that we can differentiate. So that 1 over x, we're going to write that as x to the power of negative 1. So x to the power of negative 1 plus 27x cubed. So now we'll differentiate it. So dy dx, the negative x when it's differentiated, or x to the power of negative 1 differentiated become negative x to the power of negative 2. And then 27 times by 3 is 81. So we'll have plus 81x squared. Now we want to find a stationary point, so that's when dy dx is 0. So that means when negative x to the power minus 2 plus 81 x squared equals 0. Now this is going to be quite tricky to try and solve the power of negative 2 here. So I'm going to write that as negative 1 over x squared plus 81x squared equals 0. Then I'm going to times both sides by x squared. That will get rid of that fraction there. So I'll just end up with negative 1 plus 81x to the power 4 equals 0. Then we'll move the 1 across. So we have 81 x to the power 4 equals 1. Divide both sides by 81. So we have x to the power 4 equals 1 over 81. Then what we need to do is to find the fourth root of both sides. Now the fourth root of 81 is going to be 3, plus 3 or minus 3. So x is going to be plus a third or minus a third. So we'll put plus minus 1/3. So we found the value of a. So it doesn't ask us to find the coordinates at this point. It's just asking us to find the values of a, and that's plus or minus. Well, a is a third. So we'll just write that down. Let's answer the question properly. So x or a is a third. A is a third. Okay, right, let's move on to part B of this question. And it's asking us in part B to sketch the graph of y equals 1 over x plus 27x cubed. Okay, so we're going to be using this information that we got before. We're going to be trying to work out the turning points. But before we do that, let's have a look at this equation. Is there any type of number we can't put in here where things are going to go wrong? And it's going to go wrong here if I try and put 0 into that. So I can't have x equal to 0. So that means at this point where x equals 0, I will have an asymptote. Now, if you're not sure what those are, you can always look back at the videos of sketching reciprocals or sketching graphs and have a look at the reciprocals, and that will remind you. So at this point, there's going to be a line like this at 0, basically to say not allowed. Right, so now let's find the second derivative so that we can identify the types of turning points that we have, or stationary points. So let's use this here and differentiate this a second time. So if I differentiate this again, the negative will go because I'll end up multiplying by negative 2. So I'll have 2x to the power of negative 3, and then plus 162x. And we want to see what happens when we put in plus a third into this and negative a third. so that we can identify the stationary point. Okay, let's start with plus a third, then we'll put negative a third in. So when we put plus a third in, the second derivative is going to become 2 times by a third to the power negative 3 plus 162 times by a third. That gives us 108. 108 is positive. So when x is plus a third, then what I'm getting is a minimum. There's going to be a local minimum there. Local minimum. Now we'll do the same. We will put in x equal to minus a third. So 2 times by minus a third to the power negative 3 plus 162 times by minus a third. And that gives us negative 108. That's negative. So that tells us we've got a local maximum. Okay, let's draw some axes and put in what we've got so far. So we know we've got an asymptote here on the y-axis, so we'll put that in. And then when x is a third, so maybe we'll write that down. So maybe here, a third. We've got a local minimum, and when x is negative a third, we've got a maximum, local maximum. Now, so we know where to draw these maximum minimums, we need to work out the y coordinates that this value or these x coordinates give. So we're going to plug those into the original equation. So y equals a third to the power negative 1 plus 27 times by a third cubed, and also y equals a negative third to the power of negative 1 plus 27 times by negative a third cubed. We want to get those y coordinates. So when y or x is equal to a third and we work this out, we get a y value of 4. And when we have our x value of negative a third and we work this out here, we actually get a y value of negative 4. So we're going to mark those in on the axis as well. So 4, negative 4 are y values. So that means at this point here, at the 1/3 4, at the 1/3, I get a local minimum. So that means my graph is going like this. It's going to be a local minimum. And at this point here, because it's a local maximum, my graph is going to go something like this. Now, since we've got an asymptote here, it must be the case that this graph is just going to shoot up here, getting closer to the asymptote, but never reaching it. And the same down here as well is going to shoot down there and get closer to the asymptote. There may be other things going on further here. And one way we can work that out is to look what happens to the equation as we increase the value of x here, or decrease the value of x as it becomes negative. Or we could even use the table function on our calculator to give us some sort of indication of what's happening with the graph as x goes towards infinity this way, or as x goes to negative infinity this way. So you should now be able to do exercise 12I on page 276.